All right, game on. So, other than the fact that in your instructions on the test, it told you, says write the inequality that represents the situation, or it says write the inequality and solve it. This one doesn't say that. So how do we identify that a word problem is an inequality or an equation? First of all, the difference between inequality or an equation is an equation is going to come out to only one number. An inequality is going to come out to a range of numbers that can make the statement true. Okay, so we need to look for words that's going to help that. Now, this one's not too in-depth, so going through our word problem pieces, at the end, there's the question. So the question says, what's the greatest number of rides Daniel can go on? Okay, and so using our word problem-solving technique, first we're going to identify the question, which is at the end of the problem. Then we're going to use the question to trim the fat. Now, weirdly enough, here is our unit of measure. Rides. Rides is our unit of measure. All right? That's our unit. Now, what in the word problem, what in the question identifies it as an inequality as opposed to an equation?
The alligator signs?
But it's not in there, right? The alligator signs are not in there. The what?
The greatest number.
The greatest number. Okay, so this right here is an indicator. I think the one from the test says at or exceed. Okay, words like at least. Stop doing that. Words that like at least show up. That shows you that it's an inequality as opposed to an equation. Okay? Now, the last thing we're going to do is we're going to go identify the numbers. Those are the numbers of the problem. And so in the problem, I have 25, 4, and 150. Okay? What's the unit of measure of each one of those? 25 is in what units?
The amount you had.
It's in dollars. The 4 is in what units? Dollars. And that's in dollars. Now, so since everything's in dollars, what are we looking for? Are we looking for a dollar amount? No, we're looking for number of rides. So my unit of measure is going to be in number of rides. So I'm going to use the variable R. Okay? Which of those represents a total?
150.
$1.50 is a total?
25.
25 is a total.
That's how much he has.
How do you know that?
Because it says.
All right, so, and what we've done, we haven't read the question yet other than find the highlighted part and then go circle the numbers. So, in reading the question, what we do identify is this is the amount of money, the total amount of money that Daniel has is $25. Something's always going to have a total. You have to be able to identify the totals, okay? Especially in inequalities. Because something's either going to make it come to that total, less than that total, exceed or be greater than that total, which makes it an inequality, okay? And so that being my total, let's think about the logic of the problem. Okay, the logic of the problem says that the admission, this is the admission, okay, and this is the cost per, and I think they actually use the word each ride. Okay? Now, the reason why I put the word per and each in there is because the word each right there represents what in my equation?
Rides. Mostly cost.
Okay, but what would per represent in my equation? Huh? It's changing by, oh, 1111111 or $1.50, $1.50, $1.50, $1.50, a constant rate of change, which makes it it's arithmetic sequence, but it is rate of change is also called the what? Slope. It's the slope, and yes, ma'am, it is the common difference, okay? Because those are associated. What I'm wanting you to see here is after we create this equation, it's nothing more than a linear equation. And the pieces of this linear equation that we identify as slope, y-intercept, domain, and range actually have meaning now. Most of the problem is we always start out with the problem. We say, hey, here's the y-intercept, and here's the slope, and here's this, and here's the that, and we just graph it and we move forward. But we never take it and think those things actually mean something real. So, my total amount of money is going to be $25. Can he ever spend more than $25?
No, so it's less than or equal.
Right, so then everything that's going to be in the equation is going to have to be less than or equal to 25, because if not, then he's going to have to do some other kind of services at the fair, so therefore he can pay for the ride he wants to do. Okay? So, how is his money going to be distributed or used at the fair? The first thing he's going to do when he walks in is he's going to do what?
Pay the $4.
How many rides does he have to ride to pay $4? How many rides does he have to ride to have to pay $4?
$4,000.
0 of them. He just got to walk in the gate, right? And so, if I have 0 rides that's going to cost me $4,
So you
that-
have 21 left over for the ride.
right, he has 21 to distribute, and he needs to know how he can distribute the rest of his $21. And so, from his $4, is the money going to increase to get taken away from 25 or decrease?
So like
It's decreasing from 25, right? And so on this side of the inequality, since it's decreasing from 25, it's going to be increasing from his amount spent, right?
Okay, so 1.5 times.
So 1.5
Oh, yeah.
times R. Now, this one right here, 0 rides, spending $4, that's your y-intercept.
Did you subtract that?
We're going to solve in just a second. I want to talk about the pieces of the equation first. This is your y-intercept. This is actually a coordinate of 0 rides, $4. This is the rate of change. That one is the rate of change. It's my slope, and it's going to change the number based on the number of rides that I have. Okay, so I want you to understand the equation and how it's linear. Now then, now let's solve it. Okay, so my equation is this. Solving has typically not been our problem.
Subtract
We subtract the 4.
from the 25.
So do I change the sign from that now?
No,
Why not?
Because you need to know
because
how
it's
many.
still going down.
Right.
You want to divide
I took a negative across, but it's not multiplying or dividing. Multiplying or dividing by a negative completely changes the state of the numbers. Okay?
Divide the 1.5 times 14 into 25.
Did you say 14?
21.
No,
Okay.
14
That's
is
the answer.
Okay. So the answer is 14, right? Now, here's another issue that we struggle with. We're going to graph the solution on a number line, and then we're going to write the solution in interval notation, which is another issue that we have, okay? So, my solution is 14. What is a number to the left of 14? Very good. It's the easiest one. What's a number to the right? 15, 16, 20, anything, it doesn't matter, as long as it's higher than that. All right?
Maybe like a closed circle.
Okay, it's going to be closed circle for sure because it's equal to. Good. And now we're going to check it. So I'm going to check this side first. So this is 4 plus 1.5 times 0, which is less than or equal to 25. So this is going to be 4 less than or equal to 25, right? 4 less than or equal to 25. Is that true? That is true. So technically, I don't have to check anymore. Okay? So we're going to go this way on our shading. Now, let's think about the logic of the problem in just a minute. Logic of the problem, well, the problem says that it's going to go from negative infinity to 14, and 14 is included, right? That's what the problem says. However, what's the least amount of number of rides I can go on? 0, right? So this could logically be thought of as an and problem, couldn't it? It could go to 0. Right? Because we're figuring number of rides. So yes, negative infinity to 14. 14 is the maximum amount of rides I can ride and still have money to pay for it. But I can't exactly go negative infinity rides. I'm either going to choose none of them or in between none of them and 14 to still have money, right? So sometimes the logic of the problem can change our interval notation to include 0. So the logic of the problem could have been this. It's going to go there and there, logically. Okay? Any questions?